This video is going to have a look at how do we apply geometric sequences to a compound interest scenario. So when we apply compound interest using geometric sequences, we can start off with the basic formula of Tn equals T1 times R to the power of n minus 1, but we can make a few adjustments. The first adjustment we make is that because we're starting off with a beginning balance, then our first term in the sequence is going to be the first compounding period. We're not using a T1 value, but we're instead using a T0 value. So because we're using a T0 value, at the end, instead of being n minus 1, it becomes just n. So the formula would be Tn equals T0 times R to the power of n. Now sometimes in textbooks, you might see other letters being used. So it might be An equals A0 times R to the power of n, where A would be standing for the amount. So the amount after a number of periods is equal to the starting amount times by the ratio to the power of n. So let's have a look at an example of applying compound interest to a geometric sequence. So in the example, we have an amount of 5,000 that is being invested with an interest rate of 4.8% per annum, which is compounding quarterly. So it's asking us to do a couple of things. The first is set up a recursion relation to display this information. So when we set up the recursion relation, we start off with our first term, and our first term is our starting amount, so $5,000. So we're going to start off with A0 is equal to 5,000. So remembering when we are dealing with interest, we're starting off with a 0, not a 1. So A0 is equal to 5,000, then AN plus 1. So the next amount is equal to AN, the current amount, times by the common ratio that we are multiplying each time. So before I can write down the common ratio, I need to calculate it. And because we are increasing by a percentage, it's going to be 100% plus 4.8%. But because I am compounding quarterly, I need to divide that annual increase by 4, because there's 4 quarters per year. If I was doing annual compounding, I wouldn't need to divide by anything because I'm dividing by 1 because it's 1 time per year. If it's monthly, then I'd be dividing by 12 because it's 12 times per year. So remembering when we're doing compound interest, we divide the interest rate by the number of times it's compounding per year. So that is going to equal to 101.2%, which as a decimal is going to be 1.012. So now that I've got that common ratio amount, I can write that in my recursion relation. So it's going to be times by 1.012. So the recursion relation for the example is A0 is equal to 5,000. AN plus 1 is equal to AN times by 1.012. Now I can also use that same information to be able to write a rule. And the rule for part B is going to be AN is equal to my starting amount, so 5,000, times by 1.012. And because I'm using a A0 value, so a value that comes before the first term in the sequence, is going to be to the power of n. So the rule for this example is AN is equal to 5,000 times 1.012 to the power of n. So now that I've got that rule, I can go ahead and have a look at a couple of the calculations that the example is asking us to do. Now the first one is to calculate the value of the investment after 4 years. So what I want to do is I want to substitute in a value into the equation to enable me to find that. So it's 4 years, so n is going to equal to 4, but because we're compounding quarterly, we need to times that by 4 quarters. So 4 years times by 4 quarters is equal to 16. So our n value is going to be equal to 16, and that is what I'm going to be substituting into the formula. So A16 equals 5,000 times 1.012 to the power of 16, which equals $6,051.43. Now, it's important to remember that that is the future amount that we are calculating, or the future value. It is not the interest amount. So if we wanted to find the interest amount, we would then need to take our starting amount of $5,000 away from that $6,051.43 to find the interest amount. So moving on and having a look at D, and we want to determine when the value of the investment is first going to exceed $12,000. So to do that, I'm going to substitute in 12,000 for my term value. So AN is equal to 12,000. So 12,000 is equal to 5,000 times by 1.012 to the power of n. And then to simplify, I'm going to divide both sides by 5,000. So that leaves me with a value of 2.4 being equal to 1.012 to the power of n. So when I get to this point, I can now go ahead and start substituting in different values for n until I find one that's equal to 2.4. Now, because we are starting out with 5,000 and we are more than doubling that to 12,000, and our interest rate's only 4.8%, it's going to take quite a while to get to that 12,000. So I'm going to start off substituting in some higher amounts to see what value is going to equal to 2.4. So if n is equal to 73, 1.012 to the power of 73 is equal to 2.389. So you can see that I'm below that 2.4. I haven't gone over it yet. So trying then n is equal to 74. So 1.012 to the power of 74 is equal to 2.417. So I can see that I'm now over that 2.4 that I'm looking for. So the value is going to exceed that $12,000 mark during the 74th quarter. Now to answer the question, I'm going to take that n is equal to 74. I'm going to convert that into the number of years and the number of quarters. So I'm going to divide that by 4, and that gets me to 18.5. So therefore, it will take 18 years and 6 months for the investment to exceed $12,000. So that's an example of how we can use geometric sequences to be able to answer a compound interest question.